Now, it's an immense pleasure to introduce Marcelo Viana, who is on his own a focal point to Latin American, Brazilian, and the world mathematics. And once again, an immense pleasure to lecture you Marcelo Viana from IMPA, who's going to tell us about partially hyperbolic dynamics. So.
Thank you very much, Lunil, for the presentation. Thank you, the organizers, for the opportunity to come back to Miami and give this lecture. I want to speak today about a subject which is rather classic in dynamical systems. It goes back to the 1970s, but somehow got rebirth in the mid-1990s, and I would like to tell you a little bit of what happened since then. It's a concept of partially hyperbolic dynamical system. So I start with the definition. I'm talking about discrete time dynamics, which in this context means diffeomorphisms on compact manifolds. And we say that the diffeomorphism is partially hyperbolic if one can split the tangent bundle to the manifold continuously into three subbundles called the unstable, the central, and the stable subbundles. So this decomposition should be continuous and satisfy two more properties. One, first one is that the subbundles are invariant under the dynamical system, which means that the derivative, the diffeomorphism at each point maps, say, the unstable subbundle to the unstable subbundle at the image, and the same thing for the center and the stable subbundles, invariant, invariant if you prefer. And then what distinguishes the three subbundles from the dynamic point of view is the final condition that along the stable subbundle, the dynamics should be uniformly contracting, so the derivative restricted to this subbundle has norm which is uniformly smaller than 1, bounded away from 1. The behavior on the unstable subbundle is just the opposite. The inverse is uniformly contracting, or that's the norm of the inverse is again bounded lower and bounded away from 1 at every point uniformly. And then there's the slightly more complicated center bundle, where the dynamics is asked to be somewhere in between. And what that means is that whatever expansion one sees along the center subbundle should be weaker than what one sees along the unstable subbundle. And any contraction along the center subbundle should be also weaker than what one sees along the stable subbundle. So this relation here, this inequality, again with lambda always a constant smaller than 1, should be true for every Vs in the stable subbundle, every Vc, the center subbundle, and every Vu, every vector Vu along the unstable subbundle. So that's what I mean by in between. This is usually called domination. The center dominates the stable and is dominated by the unstable subbundle, meaning that there's this inequality between the behavior of the derivative along the various subbundles. Now, this there's one special case which is relevant and actually preceded the definition, which is when there's no center subbundle. The center subbundle is trivial, reduces to 0, and in that case, one says that the system is simply hyperbolic, fully hyperbolic or uniformly hyperbolic. That was a notion introduced in the 1960s by Smale, Anosov, and Sinai. It was introduced for various reasons. There was a very ambitious set of goals in introducing this notion. The first one was to try to characterize the notion of structural stability of a dynamical system. Dynamical system, that goes back to Andronov and Kontriagin in the 1930s. a system is structurally stable if changing the dynamics, changing the diffeomorphism a little bit, doesn't essentially, qualitatively, doesn't change the behavior of the orbits. So that was the notion that was introduced by Anosov and Ya, and then was studied by Lyapunov and Peixoto and many others. And the purpose of defining hyperbolicity was to give a characterization, to express which dynamical systems have this property of structural stability. That was the goal. It was called the stability conjecture of Smale, and that turned out to be a very successful purpose. It was eventually proved by Mañé and others that the structurally stable dynamical systems are precisely the uniformly hyperbolic ones, the ones that satisfy this condition. But there was a second goal. The ambition was also to prove that, in fact, being structurally stable is a very common property, that most dynamical systems are structurally stable. And the idea of the hyperbolicity was also to allow to prove this. And that turned out not to be true. It turned out that there are, in fact, many interesting and relevant examples of dynamical systems that are not structurally stable. And of course, they are not uniformly hyperbolic either. So the way people responded to that in the 1970s, when this big news, bad news came up, was to try to enlarge the definition of uniform hyperbolicity, make it bigger, so that it could include these other examples that were being discovered, like the Lorentz strange attractor and many others. I remember as a student being a little bit puzzled by the number of proposed generalizations of the notion of hyperbolicity. There was a very clear attempt at going beyond, and still essentially almost all of them failed in achieving this. It was not possible to. But there was one notion of hyperbolicity which turned out to be one of these extensions of the notion of hyperbolicity, which turned out to be very successful, and that's partial hyperbolicity, precisely this one. And then in the beginning of the 1970s, Hirsch and Pugh on the one hand, and Green and Piessin on the other, were advancing this notion. I think the notion goes back to Anosov, but the first papers were by these authors. They were advancing the idea that one should go beyond studying hyperbolic systems and look at these partially hyperbolic ones, where one is more flexible because one allows for this center subbundle, the bundle where the behavior is only asked to be in between stable and unstable, and that this should be a path for giving more generality, a lot more generality to the notion of to the theory of hyperbolic dynamics. Now, reading those papers, I mean, they did great things, but it was not immediately clear that partial hyperbolicity was going to be so successful. That only became clear, in my view, in the mid-1990s, about 20 years later, when various results were proven by different groups of people in various parts of the world, in fact. I only pick one here to illustrate this, one of the ways where partial hyperbolicity showed itself to be a significant concept. So to state the theorem, let me introduce the definition. We say that the diffeomorphism is indecomposable, or some people prefer to say transitive, if there's some orbit which, some trajectory of the system which is dense on the whole manifold. You cannot find a closed subset which is smaller than the invariant under the dynamics, which is smaller than the whole space, the complete space. So that's clearly a relevant property for the dynamical system. And then sometime in the 1990s, I think around 1996, Diaz, Pujols, and Ulrich proved that for three manifolds, so diffeomorphisms on three manifolds, if the system, if the diffeomorphism is stably indecomposable, which means that not only it is indecomposable, but also if you preserve slightly the diffeomorphism, if you replace it by one which is nearby, it remains indecomposable. So the only way if this can happen is if the system is partially hyperbolic. You see, partial hyperbolicity, geometric property about expansions and contractions and dominations of various behaviors of the diffeomorphism appears here as a necessary condition for the dynamical property of being stably indecomposable. They actually stated the theorem for any dimension, the first time they lectured on this in '96 at the Catholic University in Rio. Then Christian Bonatti was in the audience, noticed that there was a mistake in the argument for higher dimensions. They joined forces and they came up with a statement for an arbitrary dimension, which I'm not stating here precisely, but it's a very suitable reformulation of this result, which actually holds in any dimension. At the same time, Hugh and Schuk were studying stable ergodicity, a volume preserving diffeomorphisms, and showing that stable ergodicity implies partial hyperbolicity as well. And other people were studying invariant measures of systems and realizing that partial. So there was a series of directions which eventually merged into a single effort, which brought the notion of partial hyperbolicity to light after 20 years as being relevant for understanding systems which are not necessarily within the scope of the classical hyperbolicity theory. So, why is this such an intriguing topic? First of all, partial hyperbolicity includes this more general notion, includes many new interesting examples, and I'm going to list here the three constructions of partially hyperbolic diffeomorphisms. First of all, take a matrix with integer coefficients, the matrix of S of Z, and look at the map, the group homomorphism that it induces on the torus. If the matrix is hyperbolic, which means that the spectrum does not intersect the unit circle, then this S of A is a hyperbolic diffeomorphism in the sense of Smale, Anosov, and Sinai. If you remove the assumption, if you let the spectrum intersect the unit circle, then you get a partially hyperbolic map of the torus. And not only is this S of A partially hyperbolic, but any perturbation of it is still partially hyperbolic. Partial hyperbolicity has a very nice feature of being an open condition. If you have a partially hyperbolic diffeomorphism, any perturbation, any nearby diffeomorphism, any C1 nearby diffeomorphism is also partially hyperbolic. So here you have a very simple, very natural construction of a full open set of diffeomorphisms which fall within the theory. Another one is start with flow, continuous time system, which is Anosov, which is uniformly hyperbolic. For continuous time, uniform hyperbolicity means what is written there, that the tangent space, the tangent bundle splits into stable, unstable, and a full direction. Now, instead of looking at continuous time, take the timeline map for that flow. That is an example of a partially hyperbolic diffeomorphism. And again, any perturbation of that timeline map will also be partially hyperbolic. And most of the times will not be a timeline map of the flow. So this is a second construction of partially hyperbolic maps. The third one is by isometric extension. Take an Anosov regular hyperbolic diffeomorphism on some manifold n, multiply it the way I'm describing here by creating a skew product that acts by translations on the tori on the fibers, and that is partially hyperbolic. With the tori, the vertical direction corresponding to the center direction. Again, if you perturb that, when you perturb it's no longer a skew product, but it will still be partially hyperbolic. There are now many other constructions. For a while, there were conjectures that these were the only three constructions for, at least in low dimensions, with partially hyperbolic systems. That's not true, but these are the classical ones, the ones that come to mind more directly, and show that they include situations that are well beyond the scope of the classical hyperbolic theory. The good thing, another good thing about partial hyperbolicity is that some of the features that turned the classical Smale and also Sinai theory so successful remain true in this context. Some of the important features remain true. For example, it's a fact, one of the very first facts to be proven in this domain, that the stable and the unstable subbundles in the definition are always uniquely integrable. There are unique foliations by submanifolds of M, the M space, whose leaves are tangent to these subbundles at every point for the stable and the unstable. These foliations are unique, and they have this fantastic property that they are invariant, and the leaves are mapped by the diffeomorphism of the leaves. That's the invariance property, but they are also absolutely continuous. Absolute continuity means that if you consider two cross sections to any of these foliations, and you consider zero measure subsets of one foliation, of one cross section, the image under the holonomy map is also a zero measure subset of the other cross section. So holonomy maps preserve the class of zero measure subsets. And that's absolutely key. That's the key point in the classical famous theorem of Anosov about rigidity of geodesic flow of manifolds with negative curvature. This is the key property of these foliations that makes that theorem work. And it remains true in this more general context of partial hyperbolicity. So we have new examples. We have old tools that remain available, but we also have new challenges. And the main challenge for the purpose of this lecture is the fact that, in general, the center subbundle need not be integrable at all. There may not be a center foliation tangent to EC, and when it exists, it need not be unique. And perhaps even worse, when it exists and it's unique, it still doesn't need to be absolutely continuous. Okay, so this is the place, the very obvious place to look at these systems and try to understand what happens. And that's the main topic here. I will call a system dynamically coherent. I'm not going to address specifically the question of existence of foliations, of center foliations. I'm going to look at situations where we are able to prove they exist, and we call such the systems dynamically coherent. Dynamically coherent means that the center subbundle is integrable, and so are the center stable and the center unstable subbundles. So that will be essentially an assumption which can be verified in the situations that I'm going to look at. And what I want to focus on is the geometric properties of such center foliations, sort of assuming they exist, in particular issue of absolute continuity. And at the end, I will address a different kind of results, set of results about the behavior of the unstable foliations. Okay, so from my point of view, this story starts in around the year 2000 when Shub and Wilkinson looked at this example. So you just take an Anosov map, for example, the usual cat map 2111, acting on the two torus, you multiply by the identity. That's an example of a partially hyperbolic system. In fact, it's an example of the third construction that I gave you, the isometry being the identity. And they proved that I mean, they look at this expression, lambda C of f, which is just the average of the logarithm of the derivative along the center, the vertical direction. And they proved that one can always perturb such a map in order to make this number, this is called the center Lyapunov exponent, the average of the expansion rates along the center. You can always perturb the diffeomorphism to make this number become different from zero. Of course, it is zero for the map I'm starting with for f0, because then the derivative is just the identity. But you can always make it different from zero. You can always make it positive by perturbations. And then they argued that that would lead to a sort of a paradox. The torus is foliated by circles, and along these circles, on average, the diffeomorphism, if you make lambda c positive, on average, along these circles, the diffeomorphism is expanding. It may contract at some points, but the fact that lambda c is positive means that on average, it expands. So, if you are expanding these circles, by taking iterates, you would make them bigger and bigger. And, but it's a continuous family of circles around the torus. The length is bounded. So it cannot go expanding in this family. It is preserved by the dynamics. It is expanded with lambda c of f is positive, but it cannot because the length is bounded. Now the way out of this paradox is that, in fact, in the argument that I wave my hands around, we use two different measures. One is a volume measure in the ambient, and the other is the length along the circles. And the two measures don't talk to each other. And the fact that they don't talk to each other is expressed by the fact that the center foliation is not absolutely continuous. That's their observation. If you make lambda c positive or negative, you cannot have absolute continuity. And this was the first hint that, in fact, non-absolutely continuous foliations, center foliations, might be fairly easy to get. The absence of absolute continuity might not be a very difficult situation. This was reinforced by a paper that Amy Wilkinson and Ruel published a little bit later. They showed that, in fact, whenever the center exponent is different from zero, the foliation, the center foliation, is what it calls, perhaps a bit prematurely, pathological. By pathological, we mean, and I ask you to look at the picture. On this picture, this is I borrowed from Amy Wilkinson's website, there's a foliation of, it's a torus foliated by circles, by smooth circles, by C-infinity circles. And on this picture, there's a subset of the whole torus with full volume on the torus, which consists of 1 point on each leaf. So by picking carefully 1 point on each leaf, 1 point is of course a zero length subset of the leaf, of the circle. By putting all these points together, you get a full measure, a full volume subset of the torus. That's what I mean by the two measures don't talk to each other. The volume thinks that this set is very big, and each one of the leaves thinks it consists of just 1 point. Okay. In fact, in general, there's a k, there's a number k, which in this picture is equal to 1, such that you can get a full volume subset of the three torus consisting of exactly k points on each leaf. And you see, lambda c different from zero. These Lyapunov exponents vary in complicated ways on the system, on F. But if you pretend for a second that these are smooth functions of the diffeomorphism in any physical sense, having lambda c different from zero should be fairly common. Okay, and lambda c different from zero implies lack of absolute continuity. That's a hint that pathological foliations should not be so unusual. Now, a few years ago, we went beyond Ruel and Wilkinson. We proved the following fact. There are two possibilities only in this context. Either this foliation by circles, like the center foliation, is smooth in the sense of the topology, that there are charts, there are C-infinity charts that trivialize the foliation. So either it's absolutely as differentiable as it can be, or it's pathological. So it's a dichotomy, full dichotomy. And if it is smooth, that's because, in fact, you didn't perturb your system. That's because up to a smooth conjugacy, your map is still of the form Anosov times translation on the circle. It's up to a smooth conjugacy. Your map is in fact an isometric extension of an Anosov. And this is pretty much the theme, a dichotomy between a lot of regularity, C-infinity foliation in the sense of differential topology with charts, with C-infinity charts trivializing the foliation, or the worst possible behavior you can imagine, a full measure subset of the ambient, which consists of only a finite number of points on each leaf. And the smooth case is extremely rigid. It can only happen if up to a smooth conjugacy, you are in one of these semi-algebraic situations where you act by isometry on the leaves over an Anosov differomorphism. So, in fact, this proves that pathological foliations are actually typical. What's pathological is to be smooth. Okay. Behind this, behind the proof, and doesn't show in the statement and doesn't show in the conclusions either, but behind the proof, there's a notion of a Lyapunov exponent. And this is the definition of what a Lyapunov exponent is. You take a vector, you iterate it, look at the norms of the norm of the iterates, and the Lyapunov exponent is the exponential rate of growth or decay of that norm. These numbers are well defined almost everywhere by a theorem of the Basilides. And in the arguments, there's they play the central role. And essentially, the argument is either the exponent is non-zero, these exponents are different from zero, and we can use tools from Pearson theory, from non-uniform hyperbolicity theory, various geometric tools, or the case I used to think was the difficult one when the exponents vanish, the in-between case. And for that case, we developed a tool which is called the invariance principle. And I want to give you the statement. It's a bit technical. At this level, it's a bit technical, but just to give you a little bit of the flavor of the ideas that go into this. And then I will give you other applications. So the invariance principle. We consider a map, measure preserving map, acting on some probability space, and as we call a smooth cocycle over over this map is a bundle, fiber bundle map, which acts by diffeomorphisms on the leaves. So there's a fiber bundle whose fiber is this E, whose fiber is Riemann manifolds. And the smooth cocycle is a map on the fiber bundle, preserving the fiber bundle structure and acting by diffeomorphisms on the fibers. And the main example we have in mind, the smooth cocycle, is you take your diffeomorphism, you look at the derivative. Not acting on the tangent space, on the projectivization of the tangent space, where you projectivize each of the tangent spaces at each point. So you look at this, that's the main example we have. Okay. In this context, one can define Lyapunov exponents as well. We just look at the expansion and contraction rates of the derivative acting on this fiber bundle. They are well defined by a theorem of Kingman, by the subadditive ergodic theorem of Kingman. Here I'm only interested in the largest and the smallest Lyapunov exponents, so the extreme of Lyapunov exponents. The fact that they are well defined follows from the subadditive ergodic theorem. And what I proved with Arthur Avila is this statement that may sound technical, that if you take a sigma algebra which is generating and relative to which your dynamical system and your fiber bundle are measurable, and if the exponent, the smallest exponent, is non-negative at almost every point, then it disintegrates along the leaves in a way which are along the fibers in a way which is also measurable with respect to that sigma. If you haven't heard these things before, this will probably sound very technical and abstract. It's not, I mean, we didn't invent it out of nothing. This generalizes statements by the Papier in the 1980s about he was considering linear cycles, and the main thing here. And then with Christian Bonatti and Javier Gomez-Mont, we reformulated it in a more geometric language. And this statement with Arthur is an extension for nonlinear cosines, not the action on the fibers being given by smooth maps, by diffeomorphisms, not necessarily by linear maps. So, I mean, I don't expect you to absorb the contents, but this is the technical tool that makes things work and has been used by various people. Running out of battery.
Okay, you could continue.
Next. So let me set up dwelling for too long on the technical statement. Let me show you the kind of things one can do with this tool. A very concrete example. So I'm going to consider a map induced on the 4 torus by a matrix in SL4, in SL4 Z. This example goes back to Pure and Schub in their book from the 1970s. And let's assume, so it's a matrix with integer coefficients, one eigenvalue is bigger than 1, the other one, another is smaller than 1, and then there are 2 eigenvalues on the unit cell. So if you look at the induced map, on the torus you get a partially hyperbolic isomorphism with one unstable dimension, one stable dimension, and the center subbundle, which is a dimension 2. And there are a few simple, relatively simple facts. The map preserves symplectic form, kind of an observation, an exercise. So in particular, it preserves the volume measure on the T4, F sub A. And this is something I teach in ergodic theory course. If no eigenvalue of A is the root of unit, then the map F sub A is ergodic. What Pure and Schub asked in 1977 was, is it stably ergodic? If you perturb this map, if you consider a nearby diffeomorphism, which is also volume preserving, will it still be ergodic? And it turned out that there were no tools proving that until this century, when Federico Rodriguez Hertz proved that in fact the answer is yes. Developed a whole machinery for proving that this map is stably ergodic. This was the first example that was beyond the scope of what one could do, and really introduced various powerful tools to stable ergodicity. Okay, that was his thesis with the Jacob Price. Now we looked into this, and we use the invariance principle to prove that, in fact, there are two possibilities when we perturb this dynamics. When you perturb it, either the perturbation has Lyapunov exponents, center Lyapunov exponents that are different from zero, or they are equal to zero. Two possibilities, this second. And if the exponents are different from zero, then we are in the domain of the PS interior non-uniform hyperbolic dynamics. Lots of the tools are available to study, to understand the dynamics. So the mysterious case is when the exponents, the center exponents by perturbation remain equal to zero after perturbation. And that's where we prove that if that happens, then your perturbation is not a real perturbation. It's actually conjugates the initial map. You change the diffeomorphism, but you didn't change the dynamics. You got a so the only way you can avoid making the center exponents different from zero is by essentially not changing the dynamics. By getting a perturbation which is conjugate, which is up to a global change of coordinates equivalent to the initial one. And in either case, either using techniques from Pearson theory or more standard, more algebraic notions from ergodic theory, in either case, the perturbation is not only ergodic, it's Bernoulli. So we obtain that, in fact, this kind of maps are stable Bernoulli. So the main thing here is that the case where the exponents remain equal to zero can be handled using the invariance principle. And what the invariance principle turns out to say is that that is a very rigid situation where you essentially did not change the dynamics at all. Now, to complete this series, we also proved in a more recent paper similar results for perturbations of time one maps. Remember, this was another construction of partially hyperbolic systems. If you start with the geodesic flow on the surface with negative curvature, and you take the time one map for that flow, and then you consider nearby diffeomorphism, you consider perturbations, then the center foliation for this perturbation is either smooth, say infinity, or pathological. Again, the same dichotomy. And if the center foliation is smooth, then that's because the new map is actually the timing map of a C infinity flow close to the original one. So the only way you can keep the center foliation smooth is by remaining within the very slim domain of time one maps of Anosov flows. The reason this is somewhat more difficult than the previous case is that here the center foliation, the center leaves are not compact. That creates additional difficulties, but otherwise it's formally very, very similar. Okay, so with this results, I try to illustrate some of the tools that have been developed for studying the center foliations, the properties of center foliations of partially hyperbolic maps, and how these tools rely on the notion of Lyapunov exponent and on either methods from Pearson theory or the invariance principle. In the remainder of the lecture, I want to state a result about the behavior. Now I switch gears to the unstable foliation. Okay, and I want to give refined information on how its leaves behave. So the main results that we try to, I will detail this, but give you the idea. You start with a small plaque, a small bit of an unstable leaf, and you iterate it forward. Since the unstable foliation is by definition expanding, as you iterate this small plaque, it will become bigger and bigger and will tend to wrap around the manifold. Can you give a sense to the idea that the sequence of iterates converges to something? Can you describe the asymptotic behavior of these iterates? And it turns out that the answer is yes. There's a limit in some suitable sense. And the limit does not depend on the suitable assumptions. There's a limit, and it does not depend on which block you started with. There's a canonical object that describes how these iterates, which become bigger and bigger, of small bits of unstable leaves behave as you iterate forward. And even better, the convergence to this limit is exponentially fast. That's the statement I'm going to express in more precise terms. So in order to simplify my life here, I'm going to restrict myself, and then in order also not to say terms that I can prove, I'm going to restrict myself to a subclass of partially hyperbolic systems that we call that they factor over some Anosov system. This is what the notion, this picture describes what the notion means. The system I'm interested in acts on the upper space. There's some Anosov system on the torus. There's a projection, and the projection is asked to send unstable leaves of my system into unstable leaves of this Anosov transformation, and to send the stable leaves into stable leaves of the projection system. I'll say this in a bit more of words, but that's the idea. There should be some projection to the torus, which preserves these geometric objects. So I'd say that diffeomorphism factors over Anosov. There's a hyperbolic linear torus automorphism and a continuous surjective map, which semi-conjugates the two dynamics. That's the first condition. Maps unstable leaves of the diffeomorphism upstairs to unstable leaves of the Anosov, the linear map downstairs homeomorphically, and also maps center stable leaves of F to stable leaves of the linear map. Here, the map can be taken, at this level, the map can be taken to be just a linear automorphism of the torus, a hyperbolic linear automorphism. This notion is absolutely not new. It's completely classical in topology. It's a notion of in transverse invariant measure to a foliation. It's just a family, transverse invariant measure is a family of measures defined on small cross sections to the foliation, satisfying the main property is this, the last one, that the allonomy maps of the foliation preserve this family. So if you take an allonomy from cross section S1 to cross section S2, this allonomy map measures the maps the measure associated with S1 to the measure associated with S2. This goes back several decades. It's a very classical notion in topology. Transverse invariant measure is a family of such measures defined on small cross sections to the foliation. So the theorem that we were able to prove is that if one assumes that the diffeomorphism factors over Anosov, that's the first condition. Second condition is that the leaves of the unstable foliation are dense. This is not strictly necessary, but if I remove this assumption, the conclusion will be more complicated to state. I'm taking it in to simplify the statement of the conclusion. And the third condition is that on a positive measure subset of some little bit of an unstable leaf, some very apparently mild condition, if I look at how the dynamics behaves transversely, so this is the unstable leaf, and on some small positive measure subset of the leaf, if I look at how it behaves transversely along the center stable, asymptotically it contracts. The lim sup of 1 over n log is negative. This means that the tendency transversely to this leaf is to contract. The conclusion is that in that case, the system admits a transversely invariant measure, one transversely invariant measure. And if you take any block of any unstable leaf, and you iterate it, as it grows bigger, it converges to this transverse invariant measure. Of course, I must explain, before you complain, I must explain what does it mean for a sequence of sets to converge to a transverse invariant measure. Okay. But you may not be too surprised. It means this condition here. For any cross-section, if you count the points where the iterate, the parentheses should be here. Sorry for the title. If you count the points where the iterate intersects the cross-section, and you normalize that, well, that's what's written. The intersections of these big iterate Fn on any cross-section, these points of intersection, converge to the transverse measure associated with the cross-section.
It's like a boundary of Dirac ratios.
Yeah. Fn at D intersects each cross-section on a certain number of points. You look at them as Dirac measures. You normalize by the number. Again, the parentheses should be here. Okay. You normalize by the number. You get a probability measure for each n and each cross-section. You get a probability measure which is formed by a certain number of points, weights in point. And weakly, in the sense of the weak star topology, these measures converge to mu hat S. Okay, so the mu hat S tells you how often, how many times, how often your Fn iterated D intersects that cross-section. And that happens for every cross-section. And if you want to go quantitative, instead of looking at, I mean, you're looking at weak star topology, weak star convergence, but if you restrict to Lipschitz functions, then you can go quantitative and say this happens exponentially fast. Okay? So that's the statement is that from a quantitative point of view, the leaves, big chunks of the leaves, or rather iterates of any small bit of unstable leaf, have a limit, and the limit happens exponentially fast. The exponentially fast thing is related to the last condition, to the third condition, but still it was quite surprising to us that one could get this with such mild assumptions. Okay, and that will stop here. Thank you very much for your attention.